let me explain what is deterministic finite automata. So we have to write it as DFA in short. So in my previous video, I have explained what is finite automata along with charts and diagram examples. So a finite automaton is a mathematical system with discrete inputs and outputs. So the system contains a finite number of states and can be in any one of the states. We shall now give the formal definition of a type of automata called deterministic finite automata. So a deterministic finite automata is denoted by a phi tuple Q, sigma, delta, Q naught, F. So now here Q is the set of states, that is a finite set of states. Okay, so where Q is a finite set of states. Next, sigma is a finite set of symbols. This is a finite set of symbols. Next, Q naught, that is one of states in Q, that is the initial state. Next, F, that is subset of Q, that is set of final states. That is set of final states. Here note that we have only one initial state, but we can have more than one final state. Next we define the transition function, that is delta, that is from Q cross sigma to Q. So this is a transition function. This function is called as transition function. So a DFA is initially at the initial state Q naught, and it reads an input string from left to right in a sequential manner. As I told you already, in a transition diagram, so you can identify the initial state by an arrow labeled start. An arrow labeled start indicates that is an initial state. And also a state encircled by double circle like this indicate that is a final state. Okay, that is a final state. So in a DFA, there can be many possible DFA for a pattern. Okay, so there can be many possible DFAs for a pattern, but a DFA with a minimum number of states is generally preferred. Also, in a DFA, there is only one path for the specific input from the current state to the next state. That is the main difference between DFA to NFA. So it is the simplest model of computation. So this DFA is the simplest model of computation. So with this short introduction, let me now move on to an example. So in this example, let me first check whether the string is accepted by the finite automata or not. Okay. So now what we are going to, in this example, let me check whether the string AB whether the string ABAA is accepted by this finite automaton or not. That is what we are going to check. So I have to give in detailedly how the transition function works on by taking the input symbols and how it moves on to the next state. Initially now we are at the initial state Q naught. After reading A, what happens? After reading A, we go to Q1. So after we are at the initial state, so after reading A, we go to Q1. Now after reading next input symbol B. So after reading B, what happens? Again we come back to initial state. So after reading B, we come back to initial state Q naught. Next we read A. So next after reading A in Q naught, so after reading A in Q naught, what happens? So again you go to Q1. Next in Q1 again you have to read A. If you read A, now we are at Q2, which means what? We are at the one of the states Q, that is the final state. So Q2 is the final state. Here we have only one initial state Q0, but we have two final states Q1 and Q2. Now we are at Q2, which means the string is accepted by the finite automata. This Q2 is a final state, so the string is accepted by the finite automata. Next, again we are going to verify whether the string is accepted by this FSA or not. So for that, the detailed explanation is clearly given for your understanding, okay, using the transition function. So by look at the diagram itself, I can give you how it works and whether we have to accept or not, okay. Now first we have to read, so which is we are going to check A B B A B B A. So this string is accepted by the finite automaton or not, that is what we have to check. Now we are at the initial state Q0. In Q0, if we read A, we go to Q1. So now we are at Q1. Next, again we have to read B. So we read A, then again we have to read B. If you read B, what happens? You come to Q2. Again you have to read B. So if you read B, what happens? You go to Q0. Now you have to read A next. If you read A, you are at Q1. Next you reading A, next B. Next if you read B, you are at Q2. Again you have to read B, you are at Q0. Last you have to read A. Now you are at the state Q1 after reading all the strings, all the symbols in the string. So which means this is not the final state. Q1 is not a final state. In this diagram, Q0 is only the final state. So what means? So we are at the final state, not at the final state, which means the string is not accepted by the finite state automata. Okay. So after reading the symbols in the string, if we are at the final state, then only that string is accepted by the finite state automata, otherwise it is not accepted. Construct a finite state automata over the alphabet A that consists of the symbols 0 and 1, which accept those words from A such that it consists even number of zeros and even number of ones. This is the diagram we have discussed already, you know, isn't it? So now this is the initial state Q0. So in the initial state Q0, so we have 4 states Q0, Q1, Q2 and Q3. So even number of zeros means we have to draw 2 arrows, okay. So one from Q2 to Q3 means then again it reads the same one means it come back to Q2, like that. So this FSA accepts all strings which consist of even number of zeros and even number of ones. Next one, design an FSA that accepts precisely those strings over AB that contains all number of A's. Listen, I am just explaining how to construct a FSA for this, okay. So let us assume that the states, here we have 2 cases, so that we can take 2 states Q0 and Q1. So Q0 represents even number of A's was found and Q1 represents an odd number of A's was found. And let me take Q0 is the initial state and Q1 is the final state, because the question is odd number of A's. That's why we have to take Q1 as the final state. So if it is so, we can obtain the following diagram. Okay. So this is the initial state and by reading A, it goes to Q1. Okay. After reading A, it goes to Q0. If it again reads A means, so it accepts odd number of A's. Okay. So if you read one time A, it goes to final state. Again there is an A means come to initial state. Again A means 3 times A means what happens? That is a final state. So you can check it. Okay. So next, how we can label the B? You can draw a loop like this. Okay. After reading B, you are at the same state. So there is no change. Okay. So we are concentrating only about A's. So to connect B's, so what we do? We just draw a loop like this. Okay. This is an automata accepting all A's which are in even number. The same problem, only the difference is here even number of A's. So let A is equal to consist of the symbols AB, construct an FA which will accept precisely those words from A which have an even number of A's. So previous problem, instead of even, there we have odd number, that's why we take Q1 as the final state. So in this problem here we have even number of A's. So you have to take Q0 as the final state. That is the only difference. Okay. So only difference between previous and this one is you take Q0 here as a final state too. That's all. Next. Let A is equal to set consist of the symbols AB. Define an FA which will accept those words of B which is divisible by 3. Which is divisible by 3 means you have to take 3 states. So you can take Q0, Q1 and Q2. So we need 3 states Q0. So you have to take Q0 as the initial state, Q1 and Q2. So next we find which one we have to take as final state. We need arrows labeled to going from Q0 to Q1, Q1 to Q2 and Q2 to Q0. Okay. So now the state count to the number of B's is modulo 3. So modulo 3 means Q0 is the accepting state but not Q1 or Q2. So mod 3 means, so again if you reach Q0, so that is divisible by 3. So that you have to take Q0 as the final state, not Q1 or Q2. Okay. So in the arrows labeled A do not change the state because here we concentrate only about B's modulo 3. So A doesn't change the state. Okay. That's why you have to draw a loop like this. Okay. So the finite automata here is shown below. So that is 3 states. So Q0, Q1, Q2. So you can label A, B, B. So if it is divisible by 3 means, so again you are at Q0. So you have to take this as a final state. Again A doesn't change the state. So that's why you have to draw a label for A in all states. Okay, that's all. Next, if the string BAB is accepted by the finite automata or not. First you have to read B. If you read B, you go to Q1. Next you have to read A. Then you have to read B means there is no returning state. So which means this is not accepted. Next, given DFA accepting a language of the sets of strings end with 0, 0. So what you are going to give? So you have to find an FSA that DFA that is accepting a language of set of strings that end with them. Whatever may be the string, that is 1, 1, 1, whatever that may be. So but that should end with 0, 0. So it can accept all strings that end with 0, 0. You have to base like that. You have to construct a DFA. So then here you have to take 3 states. So end with 0, 0 means you have to 0, 0 from the initial state to final state, and you have to take Q2 as a final state. So end with 0, 0. Suppose if you read 0 and then you have 1 means come back to Q0. Next if it is 0 means that is Q2. After 0 if you are having some numbers, some symbols means what happens? Again whether it may be 0 or 1, you come back to the initial state. Okay. And also you have to draw a loop like this, 1. Okay, in the initial state. So which means this DFA accepting all language of set of strings that are all end with 0, 0. Okay. So in my next video I will explain what is non-deterministic finite automata in detail along with example. If you like my video, subscribe my channel for more videos. Thank you.